For this review video, we are going to look at hypothesis testing. We're going to look at single variable z and t-tests and also their corresponding p-test variants. We are not going to look at double variable or what we've seen in some of our other chapters, whether they were independent or dependent testing. We are just going to look at single variable hypothesis tests. We're going to start off by just talking about the 5 steps of the hypothesis test. We're going to take a look at these 5 steps and then kind of talk about what we're going to do with the p-tests. So let me get to a color here. Okay, great. So the first step in a hypothesis z or t-test is to basically label the null and the alternative hypothesis. I use h sub 0 and h sub 1 for the null and the alternative. The second step is to find the critical values. Now, I say critical values because sometimes there's more than one. If you have a left tail or right tail test, you'll have only one critical value. If you have a two-tail test, you'll have 2 of them. Step 3 is to do either the z or the t-test. And for the simplicity of this final exam or review that we're doing, we're going to basically list the z-test or t-test based on sample size. So if you have a sample size that's greater than or equal to 30, you would use the z-test. If it was less than 30, then you would use the t-test. Now, we will have examples of either of both of these and their corresponding p-tests later on in this video and in the next video for the final exam. Step 4 is to draw a picture. This is going to be the picture of the normal curve, and the picture of the normal curve should have several characteristics. It should have clearly labeled the critical value or critical values. It should also have the critical region shaded correctly. And it should also have where your test value came out, so you could either reject or not reject, which is step 5, making your summary. And like on your tests and all of your homework examples, I require the summary to have at least an inequality in it. The wording can be a little bit up to you, but I at least need to see the mathematical inequality where you're comparing the z or t-test to the critical value. Now, one more item I should add to this before we look at the hypothesis p-test is we should look at what is a type 1 error. This is generally what we're going to be looking at in each of these problems. And the type 1 error is when you reject the null hypothesis when it is true. So our hypothesis testing is going to be looking at the chances of this type 1 error, and so it's important to know what a type 1 error is. We are also going to look at the 5 steps of the hypothesis p-test. Now, those 5 steps are somewhat similar, but not quite similar to the 5 steps of the traditional hypothesis z or t-test. First of all, you do have to write down your null and alternative hypothesis. These are exactly the same. Now, step 2 is exactly the same as step 3 on our traditional test, where you actually get your z or your t-test. And this is going to give you your z or your t value, and then what we need to do is convert that z or t value into a percentage by looking it on the chart. Now the word the chart actually refers to either the z chart or the t chart, and also this chart down below, which I'm going to help you, it kind of helps sort things out. Now, there's no picture in a hypothesis p-test, so in placement of this, you're going to make your decision. And this decision is usually the inequality, which is then combined with the summary. I'm a little bit less strict about this numbering system for the hypothesis p-test, but I'll show you in the next example or two how this is done. Now, the real thing we're trying to do with a p-test is to see if our sample was so egregiously rare that we would have to start to doubt whether the null hypothesis is correct. So what this usually means, and the default alpha is usually a 5% error, what this usually means is we're looking to see if our sample was in the top 5%, or basically like not considered normal to the point where 95% of the rest of the population is below or above this value. So what we have to do is use this little chart to help us. Now I'm going to put the word tail over here, and you can either have one tail or two tail tests. A one tail test can be like left tail or right tail. A two tail test would be a not equal to problem, where we have to basically see if the critical value is in either of the critical regions. So we're going to put a line down the middle here, and we're also going to have another section dividing this into 1 or 2. Okay, so if we do our z or t-test, and then after converting we look at the decimal, this is the converting from the z or t into a decimal, if we see that that decimal is less than 50%, which is usually given as 0.5 with 3 zeros, we're going to make no changes, because we can compare this value to our alpha. And if we find that our value is less than the alpha, which is usually 5%, then we're going to reject the null hypothesis. Otherwise, we will not reject the null hypothesis, because our sample group might have been different, but not different enough to have us question the null hypothesis. Now, if your decimal, let me make sure this reads a little better, is greater than 50%, which is most of the time when you do these problems, what you're going to have to do is you're going to have to subtract from 1. So let's say, for example, you end up with a percentage of 98%. Once you subtract it from 1, that's 2%. And 2% is usually less than your alpha, so you would reject the null hypothesis. Otherwise, you would not reject the null hypothesis. Let's say your decimal ended up being 70%, or 0.7000. You'd subtract that from 1 and get 30%, and 30% is not less than 5%, which is your typical alpha, and there you would not reject the null hypothesis. Yes, your sample size was different than the normal average, but not different enough to make us question if the average was correct. So, when you have a two-tail problem, you do have to double your answer before comparing it. So that means if your percentage came out to be 3%, you would then double it to make 6%. And 6% is usually not a small enough p-value to get you to reject the null hypothesis. So be aware that these two-tailed tests can be tricky. Now, what we have here is we have, if your decimal is greater than 50%, then you would have to subtract it from 1 and then double. So you would take your percentage and subtract it. So I'm going to put 1 minus the percentage, and then what I'm going to do is then times it by 2. So it's really this box here and this box. When your decimal is greater than 50%, you would subtract from 1 and then double it. So for example, if you have a two-tailed test and your percentage was 90%, you would then subtract it from 1, which gives you 10%, and double it, which then gives you 20%. 20% is usually bigger than any alpha you're testing, so you would not reject the null hypothesis. Remember, for p-tests, you're rejecting the null hypothesis when your answer is less than alpha. Now, this little chart here is really nice when you have sample sizes over 30, so this would be for your z-tests right here. But what happens if you get a t-test? Well, then you're going to have to learn how to ride the rail for the small sample sizes, which means that you would figure out where you would be between two possible alphas and decide if you are less than your actual alpha you're testing it to. Now that word salad that I just mentioned may be a little hard to follow, so watching the video here might be really helpful and beneficial. So let's scroll down and let's do the first example on this final exam review page. Also be aware that there's another example in the next video, so if one example isn't enough, perhaps getting a little bit more will be beneficial to you. Okay, so there we go. Just a little technical thing. Let me change to a new color, and let's do the traditional z-test. I will have to scroll this down a little bit to show you the fifth step here, but we're going to take a look at some wind speed and see what's working here. We've got a sample of 32 days, so that is going to be our n. So this is going to be a z-test. Now, it's important to know that on the exam, I will not be telling you whether this is going to be a z or t. It'll just say appropriate test or something of the like, because I don't want to key into the fact that you should know what test to use based on sample size. Now, what we have is an average wind speed, so this is going to be our x bar. We have a standard deviation here. Notice the lowercase sigma. That is another indication that you should probably be looking towards the z-test right there. So there's your standard deviation. And then here is your alpha. And your alpha right there is given. And again, it's pretty standard to have an alpha of 5%. And then the claim up here in the original first sentence, this is going to be our mu. This is what we believe the null hypothesis is. So the null hypothesis is going to be mu is equal to 8. Now it says here next, is there enough evidence to reject the claim? That statement in this sentence keys into the fact that we're not trying to basically state if the researcher was wrong greater than or less than, even though we can literally see that the average speed that we looked at was 8.2. We are looking to see if it's wrong. And in that situation, we just want mu to not be equal to 8 to reject the null hypothesis. Now, it's true that we found an average that's 8.2. 8.2 is bigger than 8, but is 8.2 big enough with the standard deviation to throw out the null hypothesis? Well, let's go find our critical value. If we find our critical value, we will look this up on the z-chart. The critical value, first of all, has to have an alpha of 0.05. Now, since this is a two-tailed test, and it's two-tail, because what we have is a not equal to sign, then we have to take this alpha and divide it in half. That is going to give us an alpha of 0.025. Now, I sometimes like to put an extra 0 there because what I'm going to look for is 0.0250 on the z-chart. Now, since this is a two-tailed test, I also should look up 0.9750, also known as the complement, just to see what my critical value is. And if I look at both sides, I should get the same number, one with a plus and one with a minus, because two-tailed problems have two critical values. So if I look that up, it lands at 1.96. These values in terms of because what you might have found is that it was one below and one above, depending on the chart you're using. So we always pick the critical value that's furthest away from 0. This gives us a bigger critical value, which means that it's a tougher bar to clear, and we don't want to be cutting corners in a problem like this. Okay, so it's now time to run your critical value formula, or your test value formula. So we're going to find our z-score based on the information, and what this is it's going to be our x bar minus mu divided by standard error of the estimate here, which is going to be our standard deviation divided by the square root of the sample size. These are formulas that are on your formula sheets or in your books in the corresponding units. Then we do our work here, and that lands at 1.89. So that, my friends, is our z-score. So this next picture is going to be our bell curve. And our bell curve is going to have the average at 0. This is the z-scores, the number of standard deviations away from the average. And we're going to have our critical values at 1.96. So I'm going to put one flag at 1.96 and another flag at negative 1.96. Now the critical region is anywhere inside of these shaded areas. So if our test value is inside either of these critical regions, then we know to reject the null hypothesis. But what we found is our test value is 1.89, which means that yes, our average was not equal to 8. But it was just not equal to 8. I mean, it was too close based on the sample size and the possible error. We just can't have it inside the critical region. I mean, it is close. But we should probably do more retesting to see, and after probably doing more retesting, we should see that we're not going to be inside of that critical region. So therefore, we are not going to reject the null hypothesis. So since 1.89 is less than 1.96, you could also say 1.96 is greater than 1.89, we will not reject the null hypothesis. We don't ever say that we're going to accept the null hypothesis. We just say we're not going to reject it, and that comes with an unspoken word yet. I mean, because things can change over time. The winds can kick up in that region, and 8 will be incorrect, but at this time, 8 seems to be the right number, even though on this windy series of days, it seemed to be have a higher average. It still was not high enough to say, yeah, let's throw this out. Now for the p-test of the same problem, we can just merely copy over step 1 to step 1 and step 3 to step 2. So this, for example, is going to be the null, which is mu is equal to 8, and the alternative, which is mu is not equal to 8. So we have a two-tailed test here. Now, in step 2, we came up with our z-score of 1.89. Now, the twist in this problem is we're actually going to take this z-score, which is not a percentage, and we're going to turn it into a percentage to figure out how much is below that z-score number. And so what I'm going to do is look up the 1.89 on my z-chart. So that means that on my z-chart, the z, if I look down there, this is my 1.8. And if I look over here, this is all the way to 0.09. I'm going to definitely get to a 4-digit decimal, and that 4-digit decimal is 9706. Now, step 4 is going to be to evaluate this based on the little chart I made for you. Is the percentage higher than 50%? And 97% is definitely higher than 50%, so we're going to subtract this from 1, or 100%, which gives me 0.0294, or 2.94%. Please remember that this is a two-tailed test, so that means I have to also double this number. And so because it's a two-tailed test, I will double this number, which means that I am now going to get something that's higher than my alpha. So 5.8% is higher than our alpha, and the alpha we're comparing this to is 5%. This is the same alpha over here as it is here. Now it's true I did chop that in half to get that on my z-chart, so this doubling is doing the same kind of compensation, more or less. I mean, it will give us the right result here because 5.8% is greater than 5%, so we will not reject the null hypothesis. So since the 5.88% is greater than 5%, you also could have said since 5% is less than 5.88%, but really this way that I've written it is how you're doing your main comparison. Since 5.88% is greater than 5%, We will not reject the null hypothesis. So hopefully this has helped. This is an example of doing a sample size greater than 30. So this is our traditional z-test with corresponding p-test. Now, on the next video, for our review, we're going to do a p-test and a t-test. So it's somewhat of the same procedure, but we're going to do a smaller sample size, which will be maybe a little trickier on the p-test side of things. Thank you for watching.